my name is Tyler McGaugh-DuPont. I am a student at SC4. I'm making this video for my Fluid Power and Control Circuits class, specifically on how to calculate the free air delivery of a compressor. So the compressor we used in class for this example is rated at 7.1 standard cubic feet a minute at 40 psi. So in order to calculate our free air delivery, we have to know our actual flow rate, and then we're going to compensate with a pressure correction as well as a temperature correction. So in class we hooked up a float to the compressor, and coming out of the compressor was about 2.5 cubic feet a minute. And we put that into our equation here, 2.5 cubic feet a minute multiplied by our pressure correction and temperature correction. For our pressure correction, we're using a compression ratio, which is our working pressure, plus our atmospheric pressure divided by the atmospheric pressure. And the atmospheric pressure in Port Huron is 30.05 inches of mercury, which if we convert that, that gives us 14.7 psi. And our working pressure we set to 40 because that's what it says on the side of the compressor here is 7.1 at 40 psi. So we set the pressure to 40 psi, and that gives us a compression ratio of 40 plus 14.7 divided by 14.7, which equals 3.72 psi. And we throw that into our equation here, 2.5 multiplied by 3.72 multiplied by a temperature correction. Now the temperature correction we're using for this is our ambient temperature plus 460 Rankine divided by compressed air temperature plus 460 Rankine. Ambient temperature is just the temperature in the room, and the Rankine is just another scale used to measure temperature, and 460 would be absolute zero in Fahrenheit, and it's just a constant that we are multiplying these temperatures by. And so we use 70 degrees for the temperature in the room, and the temperature of the compressed air is 233 degrees. So we have 70 plus 460 divided by 233 plus 460, which equals 530 divided by 693, and that works out to 0.764. So we plug that in for a temperature compensation, a temperature correction, and that gives us 2.5 multiplied by 3.72 multiplied by 0.764, which equals 7.1. That is exactly what we were supposed to get. And standardization is just the conditions in which the compressor is actually tested, because this compressor is not going to work the same at the top of a mountain as it would at sea level. Similar to how if you were at sea level and you were exercising and you were breathing, your lungs would not be working as hard as they would if you went to the top of the mountain and did those same exercises, because the atmospheric pressure is less at the top of the mountain, less air around, so that means that your lungs have to work harder. Same thing for compressors. So in order to make it so that all compressors are rated at a standard constant rate, we have standardized conditions that these are tested in. That way they can all be tested similarly and rated similarly. So this one is rated at 7.1 at 40 psi, and even though we have 2.5 cubic feet a minute coming out of it, when we compensate for the standardized conditions, we actually did get 7.1. So we did our math right, and they did not lie to us when they gave us the compressor. We just have to standardize the conditions, and we get 7.1. So thank you for watching my video.